So, dg by dl is this. Well, I already know d lambda by dl, d by dl and d nu by dl. So, I can derive it. Now, look for the fixed point. Fixed point means I set it to 0. So, G is like strength, they call it strength of this stuff. In Wilson stuff also we have coupling, okay, but the slight Wilson was coupling really, but here it is a G, this G they are expanding. And now we can, so one you can see that there is one fixed point is G equal to 0, right, the G plus G cube, so G can taken out, other one will be, we can simplify, G squared is square root 2 by k d. So, in fact, there is quite a bit of cancellations and there is some perturbation is also done, okay, the way we did for Wilson, oh d is epsilon expansion, okay, you can see that I will not exactly get this because this 2 will cancel with that and I think they are cancelling this 2, okay. So, there is some cancellation, I have not done this myself, I just take the result. So, the G star one correction, well I mean we can do it, I am not sure, but this is the other fixed point is for this equation is square root 2 by k d, okay. Now, if I look at graphically, it looks like this, okay. Now, for d equal to 1, okay, we can do it for different d's. Now, for d equal to 1, now you have to see which is stable fixed point and which is unstable fixed point. I did it for Wilson, I want to save time because I want to start another topic, okay. So, how do I check the fixed point which is stable or not? I look at the slope near the fixed point, okay. So, basically we compute the correction, well if I change L, then do I go away or do I come closer? So, it turns out for d equal to 1, this G1, this is a unstable fixed point and it goes here to G2, it goes there for d equal to 1. I am skipping the steps, but that is a stability analysis. We did it for Wilson, okay. So, same thing can be done here, is exactly following the Wilson procedure, but it is for dynamical system which has frequency dependence or time dependence, okay. So, for d equal to 1, G2 star is a fixed point, stable fixed point. So, I should work our dynamics here, and for d greater than 2, d equal to 2 this becomes 0 and this higher term. So, d equal to 2, this analysis is kind of failing. For d greater than 2, it turns out the G1 star this fixed point is stable, okay. So, that means the nonlinear term is not giving any correction, okay. If G is 0, then nonlinear term is not giving any correction, right, and that is like Gaussian fixed point of Wilson theory, okay. So, d greater than 2, the system behaves like a nonlinear term does not exist. So, for this equation d by dt h equal to nu grad square h plus eta, okay, and that is very easy thing for this z equal to 2 which has been derived for this equation, okay. In fact, we can do it for from this analysis as well. So, z equal to 2 and alpha is 0. It turns out for d greater than 2, this theory predicts that the surface fluctuation is basically not very significant, okay. So, alpha is 0. Now, for d equal to 1, we know that G star is square root 2 by k d, right, square root 2 by k d. So, let us substitute it here. So, fixed point means this must be 0, right, d nu by dl is 0. So, z minus 2 plus k d, G square is 2 by k d and d equal to 1. So, 2 minus 1 by so that is 1 by 4, right. So, k d cancels, this cancels. So, this is 0. So, z equal to 2 minus half is 3 half, okay. And remember alpha plus z equal to what? Anyone remembers alpha plus z equal to 2, that means alpha is half. Okay. So, that is a prediction for d equal to 1 and that matches with experiment. Okay. So, that is a triumph of KPZ equation, that these exponents only we are able to get them from theory with long calculation, but this is what we are getting from this theory. And it also tells you dimensional dependence, d greater than 2 we are not getting this coarsening, or rather not coarsening, this roughening, okay, alpha is 0. So, d I already told you about d greater than 2 and summary is, so dynamical arch. So, now this for me I was not trying to do, well, I am not giving a big lecture on surface growth, but that was an illustration of how to do renormalization group for dynamical equation, or which with frequency dependence equations. Okay. So, we can do it following the same procedure as Wilson. This is one scheme, but there are other ways to do it, but anyway this is a nice scheme, and this RG in field theory can be extended to dynamical equations. So, you are doing non-equilibrium RG in this stuff. So, result matches with experiments, and dynamical exponents are computed by this procedure. And now this one is so in, remember it was t equal to t prime is t b to the power z. So, that is b is like wave number, no, inverse wave number k minus z, and t is like frequency. So, well, omega is k to the power z. So, this z is connected with omega and k k relation. So, well, I had to do it properly, t prime t and so on. So, basically from this relation I can get this thing, relation between frequency and wave number, and z is called dynamical exponent. This is dynamical exponent. Okay. Okay. Stop.